Yes. Let's move on. Okay, hello everyone. So I'm gonna move on to chapter 3, if you don't mind. So chapter 2 is essentially the basic theory for missing data. And now section 3 is more about computation, how we actually compute the MLE and things like that. So so the main concept is the EM algorithm, but I'm going to briefly talk about the general computational tools like a scoring method and Fisher scoring method, Newton method, things like that. And so EM algorithm is the key concept, and then sometimes the E step is not easy, so then we need a Monte Carlo approach. So that is the Monte Carlo EM. Data augmentation is a little bit different story. So this is more relevant to Bayesian, and so I'm going to move on. I'm probably cover this later when it comes to Bayesian imputation. So that is the basic outline. So motivation is that if we know the likelihood function, how can we compute the MLE? So usually it's based on solving the scope equation, right? So scope function is remember the scope function is the partial derivative of the log likelihood function, right? So then this scope equation is generally a system of nonlinear equations, right? And so how to question is how to solve this solve the nonlinear equation. Okay. So a few approaches. So bisection method is that we use intermediate value theorem. So we are interested in, okay, so you can think of the graph y and x. Okay, so this is the suppose this graph is something like this. Okay, and now you want to find the solution here, right? So this is zeta actually, z-axis, and this is the y equal g zeta. And then you are interested in the y-intercept, right? I mean the value of zeta at y equals 0. And idea is basically if you start with a big range, say from 0 and some value, right? And then check the sign. One is positive, the other one is negative. Then if the function is continuous, then the solution should be in the somewhere between. So then we cut in half, right? Midpoint, and then evaluate it again. So check the sign here, sign negative and positive. So that means the solution should be in the right side of the two bisections. So then if you do this way, you can keep doing this, right? So you can reduce the length of the interval by half for each iteration. That way you can keep doing and then until you have enough, right? Enough small enough interval, then you can get the solution. So the problem with it, so nice thing about this bisection method is that you don't have to compute the partial derivative. Okay, you don't have to compute the partial derivative, but it's limited because this idea can be applicable only when zeta is a scalar. So applicable only zeta is a scalar. So it's very limited. And then method of force position, you can use linear approximation. So you have so between A and B, you linearize, right? You linearize in terms of set. So this is a linear function of set. Because you have only a first term here, and then slope. How to compute the slope? You just use so you have 2 point, then you just compute the slope using, right? This is the basically this is slope. So this is GB, this is GA. So GB minus GA divided by B minus A. That is a slope here. So this one also doesn't require computing the partial derivative. And so so we basically so set A. So A is so you use 2 point and then update one, update your set. So this is a zeta t. You have a zeta t plus 1. Then your solution, this one is a zeta t plus 2. Okay. Well, so my point is from here to here. Okay, let's do it again. So you can see this is just a approximation, right? And then idea is to view this as a, so yours, okay, sorry, let me, where, GA, did I, so put it 0, I guess, right? So let's do that, let's see. So GA plus P minus A, GB minus GA, zeta minus A equal to 0. So then you simplify. So GB minus A, GA, yeah. And then what am I doing? Oh, okay. Yeah, so basically you solve this for zeta, right? So you solve this for zeta, then you get this one. Okay, so it's not really complicated. And then point is, then from here, so this you can view it. So okay, basically originally you want to solve this, right? But this is nonlinear, so you linearize it, and so solve the linear equation instead. That is the basically the idea. And once you obtain this one, you can view it as a iterative formula for updating zeta, right? Because you have an initial point, second initial, and then so, right? So initial, second initial, and then so t plus 1, t plus 2. That is this formula. Okay. Well, so this is okay, but not really clear on how to do that in, yes.
How would you take the first two things?
Huh?
How do you pick? You have to.
Initial, okay. That is actually good. So the correct answer is that the initial value should be close to the true solution.
Well, does if you pick a really, really bad
then it doesn't work, right?
it won't do it. It won't
Right,
do it.
right. Right. So for this method to work, the initial value should be not really far away from the true solution, but you don't know the solution, right? So then it doesn't really converge, right? So if you're far away from, so if you choose wrong, in other words, if you choose wrong initial value, it doesn't really converge to the correct solution. And also you can see that this is maybe okay for scalar, but when vector zeta, this is not really applicable, right? So I guess that's probably why Newton come up with the concept of differentiation. So he invented differentiation to solve this kind of problem, right? So that's very genius idea. And basically, the idea is we can, make the length small and take it to the limit and see whether how the slope would be, right? So that is the basic idea. So then you have this partial derivative. Okay, and this is really popular method. So basically you are interested in solving this equation, right? But you don't know how to solve the nonlinear equation directly. So you linearize it first, right? So like this, and then solve the linear equation. So that is basically the idea. And then this one will give you this solution. Okay. So that is for any general, continuous and differentiable function. And in statistics, we usually interest in solving score equation, right? So then if you choose score function for the nonlinear function to solve, then it is called score equation. Okay. So then remember, this is basically partial derivative, so negative Hessian, right? This is negative Hessian of the log likelihood. So that is Fisher information method. Information. Remember, this is a random variable. Score function itself is a random variable, right? So then sometimes, so this is the idea itself is good, but because of the randomness, because this is a random variable, you may not always have an inverse. Okay, it may not be invertible in some cases. So numerically, so numerically we may want to change it. So from this one, so this is Fisher information. So inverse is very unstable. So to make it more stable, we take the expectation. Okay. So if you take the expectation, we have now script. So this is the expected Fisher information. And that is called Fisher scoring method. Okay. So that is the basic idea. Okay. So this is a graphical. I just I didn't make this graph. I just downloaded from the website, Googled, but it's still useful. So so the red one is the original function. Okay. So red one is original function. And now you have a initial value. Suppose you have any point. So you are interested in finding the solution, which is this red dot, right? So fx, so this is the point where fx equal to 0. So this particular point. So you are interested in finding this point, but you don't know this point. So idea is start with some reasonable initial point, and then compute the tangent line. Compute the tangent line, and then compute the tangent line and find out the solution. Then at so y equals 0, right? Set equal y equals 0. Then you have this solution. So this point will be called updated version of your solution. So you have an initial value. Now you have an updated one, which is x1. And because you update the point, you can start again, right? So you basically compute the tangent function, tangent line at the updated version, and then set it to 0, right? And to get your updated x, right? Updated solution. And you can keep doing that, then you can easily convert. So you can see that it goes actually quite fast, right? So the step, if you look at the step, is very, very fast. So that is actually quite powerful tool. So basically, this tangent is kind of a fast slope, right? If you have, so you want to linearize it, right? And then what is the best? Basically, the tangent is kind of best. And so, okay, so that is basically the Newton's method. So Newton is the father of physics, modern physics, and Fisher is father of modern statistics, right? So yeah, so Newton is kind of grandfather. Okay, anyway, Ascent method. So the idea is we are now. So sometimes, if you have a very nice, okay. The idea is usually we want to find a maximizer. Okay. So this is a log likelihood scale, right? This is the log likelihood scale, and then if you scope function is essentially, scope function is essentially tangent line, right? And so then tangent line itself is a nonlinear function. So Ascent method basically is that sometimes if you use this Fisher scoring method, you overshoot. So sometimes this is I don't know. So basically you have a initial point here, and then you somehow you update, and ideally you can get. So this is the true. So ideally you want to get like something converging, right? But so that that is the ideal situation. But sometimes if you shoot too much, so this is so in this case, okay, if you shoot too much, actually you go down. So if you think it as a mountain, okay, and then it will converge something like this. But if the mountain is too sharp here, then actually, even though here we don't know the other side, so we just apply this Newton method to figure out the best approximation. But turns out that this is too sharp, and so you actually the height, I mean the height of this place is lower, could be lower than what you started with, then it's not good, right? So because you want to find the maximum, but why you, so you want to go up, okay, to find, but you don't have to go down and go up, right? I mean, if you, because, so point is that in Ascent Method, we know the likelihood. So we can actually evaluate the value of the likelihood function for each iteration and make sure we climb, right? We not going down. So if this happens, so if this the updated point from the Fisher scoring method turns out to decrease your likelihood, then that means you went too far, right? So you may just reduce your size, and so that is, so basically you have originally 1. So alpha equal to 1 is always same as Fisher scoring, but now if this is too much, then you reduce it, something like that. Okay. And nowadays, actually, I don't remember in deep learning, they don't. I mean, nowadays we don't really compute the inverse of this matrix, right? I mean, just the direction, whether it's left or right, is important, but not really. We don't really care about the slope, because I think because the computation is computer is so fast, so maybe this is not really big deal anymore. Anyway, so here's a simple example. You have a logistic regression. So PI okay. PI is okay. So in this logistic regression, the density, so PDF density of the is what? Is PI YI, oh, sorry, YI XI. Okay. 1 minus PI, 1 minus YI. Okay. Because Y is either 1 or 0. If Y equal 1, you have a PI. Y equals 0, you have a 1 minus PI, right? So that's this one. I mean, PI is PI. So then likelihood is just the product of the density function, and you take the log. So if you take the log, then you have YI goes outside, and then log PI plus 1 minus YI times log 1 minus PI. Okay. So this form of the density function actually explains the form of the log likelihood. Okay. And then the second equality is just the algebra. You just simplify, then you get this one. Okay. And now question is, what is the scope function? So we want to take the scope function. So I think the idea is just to try out the algebra this time, so that you can, once you familiarize, then you can use it, right? You don't have to derive it every time. So idea, if you do that, then this is what? I equal to 1, yi xi minus 1 plus exponential xi beta exponential xi prime xi. Okay. We just take the partial derivative of this function. Okay. So that, and then you can see that this is actually pi. Okay. So then you can have this one. You get this one. Now you can actually check. What can we check? We can check whether this score function has a zero expectation under the model assumption, right? And which is true because the expectation of yi is pi. So that should be true, right? Okay. And then that's good. So then now, what is the partial derivative of the scope function? Let's do it. So and so remember, this is already p by 1, right? So then, and this should be p by p. So we want to take the partial derivative with respect to beta prime rather than beta because to make it matrix. So then we actually we don't have to worry about the first term because yi xi is nothing, right? I mean, it's constant with respect to beta. So all we have to do is to okay. So then how that looks a little bit unpleasant, but you can still try. So okay, probably the best way is we take the minus already. So then that is actually summation of I equal to 1 to n exponential, which is 1 minus 1 plus exponential minus 1. I just want to avoid the chain. I just don't want to. I just want to avoid the chain rule, applying the chain rule. So that's my way. But you can still apply chain rule if you want. So then basically you can get something like this. And then xi times xi prime. Sorry, I should have a would it be better? Okay, I can try. Okay. Not good. Okay. So anyway, something like that. And then, no, right? We already did so then you get basically this is just the constant again, and then we only have to take the partial derivative of this guy, which is something like this. And then this is actually 1 to n pi 1 minus pi xi prime. So this, in this case, we are lucky because it doesn't really depends, not depend on yi. Originally, y is random variable, right? 0 and 1 and so. But here, so when you take the expectation, there's nothing to take the expectation because it's a free of y, right? You don't have to. So if it's a function of y, then you need to compute the expectation, but here it doesn't. So in that case, Newton-Raphson and Fisher scoring method are equal. Scoring method equal, the same. And then you get this one as the your updating equation. Okay. And sometimes another way of writing, I think, is yes. So actually, this is another way is doing something like x prime v inverse x inverse x prime v inverse y. I think there's a way you can do that, but well, IW iterative reweighted least square or weighted square. I forget about that. Well, I will explain next class. Sorry about so point is that rather than programming the whole thing from scratch, there's a way you can implement it by properly determining your weight function and something like that. But I kind of forgot what is going on. There should be a way. And let's move on. Okay. So order of convergence. So this is so theta star is a limit, and you have a sequence that converges to the limit, and so this is a limit, right? And now sometimes in the numerical analysis, they are interested in understanding how fast the convergence is, and so the order usually so Newton-Raphson is order 2, and so you can see that usually this is less than 1. So then square, right? If the radius is less than 1, square of the radius is smaller, right? So that is basically the concept. So on the regularity conditions, the sequence obtained from Newton's method converges at the second rate. There's some proof. I think this is just we can just accept it. I mean, if you're interested, you can take a look, but that's not really the focus of our class. So we'll just accept it. And now later we will discuss the convergence of EM algorithm. So EM algorithm is linear. EM convergence is linear. So beta equal to 1. And Newton method, if it converges, it's a second order rate. So it's much faster. So one of the criticism of multiple imputation, I mean, EM algorithm is that its convergence is slow. Let me quickly move on. I have only 30 minutes, but I think I can cover it. So this example is relevant to actually quite related to example 2.7 that we had last class. Okay, so basically you have x and y. So you have x1, x2 through xn. And you have y1, y2, and yr, and missing. Okay. And we assume missing a random. So missing a random. So response mechanism may depend on X, but not depend on Y. So in this case, the likelihood function, so we are here, we have 5 parameter, right? Mu1, mu x, mu y, sigma xy, sigma xy, yy. 5 parameter, 1, 2, 3, 4, 5. So if we observe X and Y together, we have 5 parameters. So that's from I equal to 1 to R. And then from R to N, we only observe X. So we have a 2 parameter. And so we want to maximize, find the maximum MLE, right? Find the MLE. So if you think about this way, finding the MLE has some computational difficulty. And we want to avoid some, so you want to find, so and then T.W. Anderson, he's at Stanford, right? So he actually come up with a very interesting idea. So idea is very simple, very clever. So joint PDF of X and Y is a marginal PDF of X times conditional PDF of Y given X, right? So, and then because this is normal, the marginal and conditional are very easy to derive, right? So in the marginal, you have a mu x sigma xx, and conditional, you have a beta 0, beta 1, x, and sigma EE. And sigma EE is, so you basically have a reparameterization. So you have a mu x, mu y, sigma xx, sigma xy, sigma yy, right? This is one set of parameterization. The other way is mu x, mu x and sigma xx and beta 0, beta 1, and sigma EE. Okay, so this one and this one is 1-to-1. If you know one set, you can construct the other one, vice versa. Okay. Sigma EE. Mu x sigma xx, beta 0, beta 1, sigma EE. Okay. So what is the big deal about this? Well, so now you can express this joint density as a product of conditional, marginal, and conditional. Okay. And then this is what? This is marginal. Right? So that you can actually combine. So you can combine marginal here, and set aside. And then this is a separate, right? So this conditional leaves alone. So that actually gives this kind of factorization. So you have a marginal density from I equal to 1 to N, and then conditional density from I equal 1 to R. Okay. And then why this is useful? Well, you can see that because the likelihood is factorized, you can separately maximize, right? You can use the whole sample to obtain the MLE for the marginal density parameters, right? And then you can use the complete case only to compute the MLE of the conditional parameters, conditional distribution parameters, right? So that's also, easy. So that's essentially this. So mu hat x and sigma x. So here, so this is the marginal parameter, right? Marginal. marginal density parameter, you have a subscript n to emphasize that we use the n observations to compute the MLE. And then this one is a conditional density. Right. So that means you have R in the subscript. Okay. So where the subscript R denotes that the statistics are computed from the R respondents only, and subscript N denotes that the statistics are computed from the whole sample of size N. Okay. So that's not the end of the story. We need to transform back. Okay. So because we are, well, even though they are, right, even though two parameterizations are one-to-one, this is original parameter. This is new parameterization. Okay. So if you are interested in finding the MLE of this guy, so we are not, so suppose I'm really interested in computing the MLE of the mean of Y, then we use this one and then use this to construct, right? So that is the final step. Basically this. So we just use other parameterization. So see the relationship between mu I and so from one to, so this is the parameterization, right? And so we use this MLE to obtain the MLE of the mu I. And then remember, these two are based on R observations. While this is based on N observation. Right? And so this is basically C. Okay. And then because beta 0 is this one, right? Beta 0 hat is Y bar R minus beta hat 1 X bar R. So then we put it here to get this. I'm sorry?
Is it X bar N or X bar R?
Beta 0 we use R.
Okay,
But X bar, you have X, we use X bar. So here actually we use X bar N. So yeah. So actually this is kind of interesting because we have something like this. 1, 2, so we have R, we have N, right? So this is the data structure. We have N observation of the axis and R observations of the Y. So basically this is a missing data, right? We have a missing data here. And what this P.W. Anderson figured out is that the MLE, how to compute the MLE for the marginal mean of Y, mu I hat Y, is Y bar R plus beta hat 1 X bar N minus X bar R, right? Which is actually 1 over N, I equal to 1 to N, yi hat, where yi hat is beta 0 hat plus beta 1 hat xi. So So what is the interpretation of this guy? So interpretation of this guy is that you use respondent as a training set to build a model. Okay, so use R observation because you observe X and Y together in R observation. And then because you have both observation, you can train, you can build a model. Okay, and then use that to predict. Okay, to predict. That is this one. So that is turns out to be the best way. Okay. And this is so actually this is a very popular concept in survey sampling too, regression estimator, and all come from the all come back. So this is the very first idea on this direction. Okay. So this is the so here's a remark. So regression estimator can be expressed as the sample mean of the best predictor of yi. Okay, so you can actually either predict only for the missing data, or you can predict the whole sample same, because the residual among the respondent is 0, right? So because of this, these two are the same. Doesn't it's not really different. So yeah.
Why the base predictor of y? Is it because it's normal?
I'm sorry.
So you wrote the regression estimator can be expressed as a sample mean of the base predictor of y. So why base predictor? We are just using a regression.
We have a conditional distinction, right?
So is it because normal?
No, right. It's conditional mean. Okay, so that is this one, and you can, and we already know. So here's a interesting point. So now, question is, if you are interested in computing the variance of y, right? And we actually already studied from example 2.7 because this guy is the inverse of the observed information matrix. Okay, remember you have a 2 by 2 matrix, and this should be the this part. There's some additional, I mean, you can also directly derive this using Taylor expansion, but I will cover that in chapter 4. So we can wait a little bit, but the more important thing is to understand the concept and the interpretation of MLE. So basically, let me record. So whatever we can explain. So among y, right? I mean, in the variance of y, we have some component that can be explainable by x, right? That's this part. So if we can, those components can be explained by x, has a sample size, effective sample size n, while so this is a kind of a error sum of scale, right? I mean, so means of MSE. So that is not really explained by genuine error part, which should have the sample size, effective sample size R. So that is the basic idea. Okay. So another one. This is the same. It's actually it's also interesting topic. So you have a binary category. So 0, 1. So y1 is 0, 1 binary variable. y2 is also 0, 1 binary random variable. Okay, that's it. And then what is the probability distribution of the vector? This one should be this, right? I mean, so because we know that y1, this vector, random vector y1, y2, supposed to have one of the 4 possible values, right? So we know, this is all I know. This should be one of the 4 possible values. So that means what is unknown, what we do not know is the corresponding probability. We don't know the probability. So that's the parameter. Okay. So this is the parameter, and this is the possible value. Okay. And we have data. And the data we have is a partial missing, right? So from 1 to R, we observe y1 and y2. But from R plus 1 to N, we only observe y1. So we have partial information. Okay. So then question is, what is the observed likelihood? Okay. So original answer is something like this. You have a I equal to 1 to R, and then joint density. Okay. And then what is this, by the way? So what is the joint density? Well, you have 4 possible values. So pi 1, 1, you have a y1 times y2. Pi 1, 0, you have a y1 and 1 minus y2. And pi 0, 1, you have a 1 minus y1, y2. Pi 0, 0, you have a 1 minus y1, 1 minus y2. Because we know, right? Because y1, y2 are all either 1 or 0. So that means this product, y1, 1, right? Y1, y2. So this product is either 1 or 0, only one place. Okay, and this should be the corresponding probability. So you can use that to use it to here. And then marginal, same story. You now have a pi, because you only observe y1. So you basically have a pi 1 plus y1. So 1 plus, okay, let's do it again. So you don't have to pi 1, 1 plus pi 1, 0, y1 times pi 0, 1 plus pi 0, 0, 1 minus y1. Should I, let me write it a little bit more carefully. So let me write it again. Pi, because we only know y1. So pi 1, 1 plus pi 1, 0, y1, pi 0, 1 plus pi 0, 0, 1 minus y1. Because so this is the probability for y1 equal to 1. This is the probability for y1 equal to 0. That's it. But if you think of putting all these density function to this function, very complicated, right? It's a very unpleasant. Okay. So we're gonna use alternative approach. So idea is consider a different parameterization. So alternative parameterization essentially are factorized from marginal and conditional. So joint equal is marginal density times conditional. Okay. So marginal means y1 because y1 is always subject. So for the marginal density, we just y1 is about y1. So y1 is either 1 or 0, right? I mean, so y1, so that is the parameter, basically pi 1 plus y1, 1 minus pi 1 plus y1 minus y1, something like that. So that is this marginal density. Conditional density, okay, here's some question I can ask you. So here, in this solution, how many parameters do we have? 3, right? Because this penalty should add up to 1. So the freedom, degree of freedom we have is 3 only, right? That means if we want to make a one-to-one parameterization, the other parameterization, we should have 3 parameters. So this is the 3. This probably y1 equal to 1. Because if I know y1 equal to 1, that means I automatically know y1 equal to 0, right? And then conditionally, I have 2 cases, y1 equal to 1 or y1 equal to 0, conditionally. And then conditional on this, I have only 1 degree of freedom, right? So that means I have 3 parameters. So basically we have a, see, pi 1, 1 is pi 1 plus times pi 1 given 1. Pi 1, 0 equal pi 1 plus times y, 1 minus pi 1 given 1. Pi 0, 1 equal pi, 1 minus pi 1. 1 minus pi 1 plus times pi 1 given 0. Pi 0, 0 equal 1 minus pi 1 times, it's confusing. Okay. So y1 equal to 0, y2 equal to 0 means, probability means y1 is equal to 0 probability times conditional on y1 equal to 0, we want to have y2 equal to 0. So that is this. I'm sorry? When we want to use this? Yeah. Okay, that's a good question. So, that is actually the main topic of the course. So, when we have a monotone missing pattern, so we explain this. Monotone missing is something like this. We have a y1, y2, y3. We have a something like monotone. So subset response is a subset of the other, something like that. So if in this case, the parameterization is conditional on y1, and y2 given y1, and y3 given y1 and y2. this parameterization is really works very well. That simplifies the computation greatly. So that is the point, but I'm not sure whether I have enough time. Okay. What I can do, I have actually I have 5 more minutes. Okay. So so idea is okay, the plan is to use this relationship, right, to where? To plug into here. So that's a little bit dirty in terms of the algebra, but let's if you can follow this, so the logically we have a y, I equal to 1 to n, the marginal distribution of y1, okay, and then I equal to 1 to n, we have a conditional distribution of y2i given y1i. So that is the trick point. So this guy, right? This is joint. So this is joint. Joint is a marginal times conditional. Okay, and this conditional actually can be combined. So this marginal can go combined together to get from 1 to n, and then conditional is a separate. Sorry, this should be. I made a mistake. Yeah, right. So this is not correct. Correct answer should be I equal to 1 to r. Okay. So if you can accept this argument, then we can see this parameter has only to do with pi1 plus, right? So in terms of this parameterization, what matters here is a pi1 plus only. Okay. So basically we have a, let me let's calm down. So pi1 plus y1i, 1 minus pi1 plus 1 minus y1i. That's it. Okay. So we don't really have to worry about this. Now, let's take a look at this carefully. This one, actually, we can distinguish the, so this is, first of all, we are only using the fully observed, right? First R element, and then we can actually partition the fully observed data into 2 parts based on the value of y1. So we basically y1 equal to 1 case and y1 equal to 0 case. We separate them out because for y1 equal to 1 case, it only differs. It only matters with this pi1 given 1, right? And then the other one, pi1 equal to 0 case, it only matters with pi1 given 0 parameter. So end of the day, surprisingly, we have a very nice factorization. Okay. See, remember, this one, the first one is a full sample using marginal density. This one, we use only respondent and only y1 equal to 1 case. This one, only respondent and y1 equal to 0 case. That's it. And then because of this factorization, actually, the maximization is very easy, right? So you can actually compute the MLE by, so this is kind of the result end of the day. Because it's a binary, right? Binary, binary random variable binary distribution. So the MLE is just a sample mean of the cases. So here, just a sample mean. Here, it's a sample mean of the respondent among y1 equal to 1. That is y1 equal to 1. We give y1 equal to 1 already. And then take the average minimum. Here, among R1 to R, y1 equal to 0 cases first. So that's why we have 1 minus y1 in numerator and both numerator and denominator, and take them. So that is the solution, MLE. Okay. So then once you obtain the MLE of this new parameterization, then you can transform back to the original scale by using this formula. So that is the basic idea. Okay. So that pretty much take care of the this section, but I will stop today here, and then I will just wrap up and move on to EM algorithm next week.